Okay, so when we talk about vector data analysis, so far we discussed about the raster data and vector data models. We talked about GIS software in general, and today we'll be talking about vector data analysis. When it comes to vector data analysis, there are several techniques that are commonly used. One such thing is buffering, and the other one is overlaying. Now, I have organized the lecture series or the lecture slides based on those two, mainly buffering and overlay operations. And then we have feature manipulation and also spatial analysis. We'll be moving from here to spatial analysis, where we discuss about Moran's index and things related to spatial analysis. I will start with explaining the learning outcomes of this lecture. After following the lecture, you will be able to define buffering, overlay, and spatial analysis techniques. We will talk about what is buffering, what is overlay, and what sort of spatial analysis techniques are available. Then the second learning outcome is analyzing the applicability of vector data analysis to different disciplines, different applications that you want it to be applied. Once you understand the applicability of these techniques, you should be able to apply vector data analysis techniques and feature manipulation for data management and analysis. We will talk about how to apply vector data analysis in your applications as a separate lecture on a hands-on session. We'll talk about buffering. In GIS, buffering is a technique used to create buffer zones. Buffer zones indicate, for example, if you have a point like this, a buffer zone means a certain zone that demarcates a distance from that particular point. So in this technique, we create buffer zones for points, lines, or polygons. The method generates two areas, one that falls within a specific distance of the feature. So a zone like this that is particularly in a certain distance from the feature. And we call this the buffer zone. Anything that lies beyond the buffer zone also is here. And as I said, buffer zone creates two different zones, one that lies inside a particular distance and one that lies outside of it. So this part is the buffer zone and the other part is beyond the buffer zone. The buffer distance, if you take a look at this distance, the distance from the port, I'm particularly focusing on a point here. So this is the buffer distance D. The buffer distance can be constant, which means it does not change. The distance remains constant. If you give D equals 5 meters or 50 meters, it will be the same throughout. That's one form of buffer distance. And also you can create multiple rings around a particular point. Let's say you have 5-meter rings, and then you have 10-meter rings and 15-meter rings likewise. It can vary depending on your requirement. Also, these are called buffer rings, and you can decide what sort of a distance they are. Let's say not only 5 meters, it can be any distance as you wish. In the multiple ring case, you can also have buffer zones that are not in consistent increase. Let's say this is 5 meter, but you can have another buffering maybe from 7 meters as you wish. Constant distance buffering has a uniform width, like 5 meter. For instance, let's say you want to create this around the water source, you may require constant 100 meter Buffering for environment protection. Let's say you have a well like this, and the well is located underground. So this is the well. And there is a health concern that you need to have 100-meter buffer zone where you cannot have any septic tanks or toilets or such cases. So you have 100-meter buffer. In such case, when you look at it from the top, you would see something like the well, and then you have the 100-meter buffer like that. This is applicable not only just for the environmental case, it can be applied for marketing, can be applied for business, for a particular shop that is near a school, or something like that. You can also think about variable distance buffering. So I was talking about constant distance buffering. Then you have variable distance buffering. In the case of variable distance buffering, it is used for specific criteria like different land use zones around riverbank or varying widths based on soil quality, right? For example, you may need to think about variable distance buffering like you have a school. So this is your school. And if you want to get something, okay, let's say this is your school. And if you have a certain guideline that says you cannot have a liquor shop near 50 meter of the school, so you create a buffer zone with 50 meters radius in both sides. So this is one constant distance buffer. There can be another buffer that says, all right, you can have a particular shop, let's say, not only a liquor shop, that we can look at something else like, for example, betting zone. So betting zone. If this distance is different from 50 meters, there can be another buffer that goes maybe for 20 meter or something. So there can be another buffer that goes for 20 meters. In such case, you have variable distance buffering. And also, this may be the case if you are running along a road, and for each intersection or a station that you stop, there can be a buffer that is like within 20 meters you can't find any shop, or within 20 meter or 30 meter you cannot find a certain, let's say, a place to stay or place to eat, place to find water, likewise. Constant distance buffering, variable distance buffering, and multi-ring buffering, they all happen to be in the same analysis. So you can create multiple buffer zones around a feature, often used for evacuation planning. Let's say you have an earthquake happening and you need to tell people to evacuate, and you can see the certain effect of a location may be felt by a certain distance. In maybe the location A has the highest damage, location B has the lowest damage, etc. So in that case, people feel it in different directions and different distances. So you can go for multi-ring buffering together with variable distance buffering as well. So depending on the applications, you can create different buffer zones around different features. I was explaining mainly about points. You can actually create buffers for lines and polygons as well. When you create a buffer for points, it looks like a circle. But when you create a buffer for a line like a road, it can be either like this, that covers this area all together with a certain fixed distance, or it can have corner points becoming more round like that. So it depends on how you want your buffer to be. That's for the lines. In the case of polygons, you can have a house or a building like this with corner points. Again, as I said, the buffering can be going with corner points, or it can be going with some shapes like circular shapes, depending on your requirement. So in all these cases, what I explained was creating buffers regarding different spatial points, spatial lines, and polygons that you find as vector data. Now, I have mention the applications of buffering. You can use buffering to identify suitable sites for projects by excluding protected areas. For example, let's say you have a road like this, a line, and there may be a particular building with some value, some ancient building or a national heritage or something. And maybe sound is a hazardous thing for this building. Maybe it has some sensitive things. So the government is telling you need to have a buffer, maybe 50 meters from this. You cannot have any record bar or music shop or anything like that, or any concerts for that thing. So you have to honor that, and then you create the buffer, and you have to make your decision that lies away from that particular zone. In the case of hazards, like you have seen these hazardous points in space, there may be a chemical or a radioactive decay or something in a particular area. So it says beware of that particular hazard and stay away from that location, maybe a certain distance. So identifying suitable sites as well as hazardous zones, excluding protected areas. Creating buffer zones for hazard management and evacuation planning. Now, evacuation planning is also something that you have to think of when you are developing spatial analysis. You are understanding spatial analysis from disaster mitigation point of view as well. If you look at buildings, in some buildings, you have a route, a certain route for exit, and also there is a certain buffer zone along those routes where you cannot put certain dangerous items, because if you are following this route, if you have any item that may be blocking your way, then it's seriously affecting the evacuation planning. So that is also another important use of buffering. Then, of course, protecting wildlife habitats, minimizing environmental impacts, all these things are part of buffering. Now, when you think about buffering, you should be able to now understand, relate your applications and things that you encounter every day to what you think of buffering, like what sort of applications you can have with buffering. Again, you have overlay analysis. In the case of overlay analysis, it is a technique that combines geometries and attributes from two or more spatial layers. So you can have point in polygon. In this sense, you have a point, something like this, and a polygon, right? The point may be inside the polygon or outside the polygon. Mainly when we are thinking about overlay, we talk about inside that particular polygon. Again, where you can be thinking of a line that goes like this. So this part is inside the polygon. That is also part of overlay operations. Then we can think of polygon to polygon overlay, where you have one polygon, then maybe you have another polygon that goes like this. So this is also somewhat an overlaying area. The name suggests, it's an overlay operation. The interesting thing is, in the overlays, it creates a new layer with data from all the input layers. It's an essential tool that helps identify relationship between different features and data sets. Now, if you want to find out whether if you are looking at a road here, if you are interested in whether this road is going through, maybe this is a land area. If you want to find whether this road is going inside the land area, that's also one type of an analysis that you may be interested in, right? Now, let's kind of have an idea about what this point in polygon method. So this is one type of an overlay analysis. Now, this method identifies which polygon a point feature falls within, right? For instance, you can determine which administrative boundary a wildlife observation point belongs to. If you have, maybe this is your point and this is the land, so you need to find out if your particular location belongs to a certain territory. Let's say there are several territories here and there. So if you need to find whether this particular point, this is your point, whether this point is in block A, block B, block C, or block D, if you want to find something like this, we use an overlay operation called point in polygon. In the case of line in polygon, the lines are intersected by polygon boundaries. You have the polygon boundary now. In the case of that, if I were to draw it again, you have the polygon boundary, and then you have the line that is intersected with the polygon boundary. It creates new set of polygons that contain data from, give me a second. Right. So it shows the part of the line that lies inside the polygon, right? Now, what is polygon to polygon? In the case of polygon to polygon, you would find combination of two or more polygons creating a new set of polygons that contain data like this. So this is just two polygons in the first case, but because they are interacting, you have multiple number of polygons created because of the overlay operation. Now, this can be done for vegetation zones with administrative boundaries to determine the extent of each vegetation type in different regions. Now, if you have previously done some image analysis, maybe some of you are interested in image analysis. Some of you might have done some operations in maybe some software for image processing, where you have two images. Let's say you have one image like this, and then maybe there is a part of that image that you need to maybe cut, so that maybe there's another part, maybe a boulder or something in front of you, and you need to show the boulder as an object in front of you. So what you do is you do the overlay operation and make sure that this part is just boulder, not the hat that you are wearing in this case. So those are polygon on polygon type of overlay. So the interesting thing is that you can think about overlay operations, point in polygon, line in polygon, polygon on polygon, various types of overlay. But the techniques involving the analysis typically can be included under union, intersection, symmetrical difference, identity. When I tell this, you should be able to remember that we did similar things in statistics. In statistics, if you remember, we did the Venn diagrams. So you have Venn diagrams, and if you have two sets, for instance, if this is set A and this is set B, the intersection of A and B can be written as A intersection B, and this is the part where you have the intersection. And it's the same thing. In an overlay operation, intersection is simply the area where both polygons lie. So this particular point means the both polygons have a common area in this particular section. Union, on the other hand, if you remember, includes everything that belongs to A or B. A union B. So the same operation is here. The union indicates anything that belongs to A or B. Now, in the case of this kind of a scenario where you have two polygons, let's say this is one polygon and this is another polygon, this may be one administrative area. This may be a vegetation area, maybe some forest or something. You can easily think of this one as, like, let's say this is Sabaragamuwa province, and then there may be another province that goes like this. Maybe this is the Uva province. So this may be Sabaragamuwa province, this may be Uva province, and this vegetation section may be a forest. So in the case of this vegetation section, the forest, that belongs to both Sabaragamuwa province as well as Uva province. So you can see that if you look at the intersection of the two admin boundaries, the union A union B belongs to this part as well as this part. So A union B indicates the vegetation section. So symmetrical difference is actually when you have something like this, right? So when you have an intersection like this, you can get the symmetric difference by simply getting part of it out, A minus B or B minus A. So these are set operations actually applied on various sets, and it's the same thing. The naming convention is the same. Identity is also the same. The good thing is you don't need to worry about overlay operations. You don't need to do them manually. The software will do it for you. But if you understand the concept only, if you do not understand it, then you don't know what to apply when the need comes. Sometimes you might need to apply union, sometimes you need to apply intersection, but depending on what you really need, you can use the software for the overlay operation. Now, you have the second or the next stage is feature manipulation tools. You have several feature manipulation tools, and feature in the case of feature manipulation tools, these are very important for managing and refining geographic data. We use this often actually to adjust and transform spatial features to meet specific project requirements. For example, dissolve, clip, select, eliminate, split. These are common type of feature manipulation. Let's look at one by one. In the case of dissolve, we aggregate features with the same attribute values. Let me give you a simple example and let's move on. Imagine that you have an area like this. And this is your, I'll draw this carefully as possible. This may be one boundary, another boundary, and another boundary. So for the simplicity, let me name them as 1, 2, 3, 4, 5, and 6. So these are admin boundaries or some polygons. If I name this, I would say polygon ID. You have 1, 2, 3, 4, 5, and 6. For each of these polygons, imagine that you have a certain attribute. So I can name the attribute, let's say the ownership. If I say ownership, I can say polygon 1 belongs to John. Then polygon 2 belongs to, let's say, Martha. Polygon 3 belongs to maybe, let's say, Joseph. And let's say polygon 4 belongs to Sahan. Then polygon 5 belongs to Nadun. Then polygon 6 belongs to Cheryl. So imagine that these are the ownership. So if you look at this, all these names are different. So John, Martha, Joseph, Sahan, Nadun, Cheryl, these are the owners of these lands. So let's say that after, now this is the old ownership, okay? Now what will happen is with time, so let's say Joseph wants to leave the country and he sells this to John. So we can update the new ownerships. If I would say you have the same new ownership for John, but now the lot 3 is sold to John by Joseph, right? And Martha is also leaving the country and Martha is selling it to Sahan. Imagine now Martha is selling the land to Sahan, right? And Nadun and Cheryl, they are going to be the same. They are still living in the country. So afterwards, right? Now, if you want to update this list, what you need to do is to aggregate features with the same attribute value. In this case, now the land lot is no longer 1, 3. If you draw it now because polygon ID 1 and 3 now belongs to John, because Joseph has sold it to John, the land becomes like this. So there is no 1, 3 anymore. It's just a single land. And in the case of Martha and Sahan as well, Martha has sold it to Sahan. Because of that, now the landlord becomes something like this. We simply call this one dissolve operation, because you, instead of various polygon IDs or various disaggregated values, you make them to a single value or a same attribute values by rearranging the polygons. So that is dissolve operation. If you need to update land names, or if you have, let's say, if you are in a marketing campaign and you did some marketing analysis for a certain attribute value over the region, then you can join those sections and make them a single section. We call this dissolve operation. Clip creates new layer with features falling within the extent of a polygon. Now, clipping, I'm sure you have heard of this one if you have done image processing. Clipping is very simple. If you have some land lot like this, if you need to, let's say, you have a buffer zone. So this is your school or some other building that requires the buffering. So when you create the buffer, and this is your buffer. So this is a 50-meter buffer for the school. Now, let's say this is land owned by someone. Let's say land owned by the state. So if this particular land needs to be given to the school or given to this particular buffer zone, then we can clip it out. So clipping means you just remove this part where the other polygon intersect. That's it. Creates a new layer with features falling within the extent of a polygon. That's what we call clipping. Selection means extracting features based on query expressions. Let's go back to this example where you have now new ownerships. Polygon 1 and 3 no longer belong to John and Joseph. It's actually belong to John. So if you want to find, you need to extract features based on query expression. Let's say I want to, I want to extract the land which belongs to John. So if I do this query, I can say select John, then attribute value John will be selected in all these cases, and land lot 1 and 3 will be shown selected or highlighted. So you can do operations on the selected features. That's what we call select operation. Eliminate means removing features based on logical expressions. Of course, this is just simply applying whether any feature that is greater than 2, greater than 3, or whatever logical operation that you need to apply, you apply on that and you remove them. Splitting divides layers according to predefined geometry, which means, let's say that, again, coming back to another example, you have a land like this, and maybe there's a highway going on. So there's a land project development going on by the government, and the government says, now you need to divide your 1 acre land into 2 different sections because the road is going through it. So you split the land based on this feature where you have the 2 boundaries, right? So that's the idea of splitting. Now, these are selected manipulation tools and operations. There can be many other, depending on the requirements and the way that you use them. But in general, dissolve, clipping, selection, elimination, splitting, those things are very, very much used in your everyday operations. Now we come to a very important halt in spatial analysis, where we examine the arrangement and distribution of spatial data. In this lecture series, I will be focusing on Moran's index in general, while I explain to you about nearest neighbor analysis, replace K function, and other things as well, but I will mainly do the Moran's index, and you will learn how to do calculations based on the Moran's index. But I'll give you a little heads up about nearest neighbor analysis. In the case of nearest neighbor analysis, this statistical tool measures the distance, right? Distance between the features and its nearest neighbor. So distance between the feature and the nearest neighbor. So neighbor. So imagine that you are here. This is you. And it's raining. You don't have an umbrella. And there is a summer hut somewhere here. And there is another building somewhere here. So the nearest neighbor analysis indicates you do the analysis to find out if you measure the distance from yourself to the summer hut and from yourself to this building, what will be the closest distance between the feature and the nearest neighbor. That's basically what nearest neighbor means. But the interesting thing is there can be weights, right? So maybe you need to go to the summer hut after going through a rough terrain. Maybe the building is straightforward. You have a road that you can go there. So in such cases, you will be updated with new information, some weights, and weighted nearest neighbors are there. Now, when it comes to Moran's index, in the case of Moran's index, I will not talk about Moran's index in this lecture. We will go into details of this one in the next lecture where we go very deep into Moran's index. But I'll just simply tell you what this is. Imagine that you are looking at a certain distribution. Maybe you do a marketing campaign, and this is the location where you started your marketing campaign. So the buffers, that when you create the buffers and you understand, you do a sampling survey to find out whether that marketing campaign was worthwhile, whether what you intended was achieved. So you find out now this is the marketing campaign location, and the land is, or the area is separated into different places like this. So you do the analysis to find out whether your marketing campaign was successful. And if you analyze the values from here, here, in all these cases, maybe you are getting a certain value. Maybe let's say you are doing a marketing campaign on a certain perfume. And if you ask the perfume name, whether you know this perfume from different places around that area, different people might say, okay, I know the brand. Then you can ask, have you learned it from our marketing campaign? Or you can ask, have you known this before? We can create a questionnaire. So you get the questionnaire, and then when you analyze it, Moran's index tell you whether there is a relationship between the adjacent areas or adjacent locations to a given location, and whether there is a correlation between these points. For example, is the marketing campaign so successful that the locations adjacent to the marketing campaign locations have a high number of awareness? But let's say if you do the analysis from somewhere here, maybe these people might not know about the perfume, which means the strength of this particular correlation is only very short distance, like adjacent only. So there are various techniques that we use in developing Moran's index. There is contiguity metrics, etc. So we'll talk about that when we deal with Moran's index. Replace K function works in similar manner, and in the hotspot analysis also we use similar techniques like Moran's index. We call this local G statistics. It is part of statistics. Now, in the next lecture, I will talk about the feature selection methods, feature operations, feature manipulation techniques, and also overlay operations, and also applications of buffering as a single project.